All right, so let's get right into it. We have a major mystery on our hands. We're starting to use these super advanced AI agents for incredibly important jobs. But the thing is, sometimes they just fail. And for the longest time, we haven't had a clue why. So in this explainer, we're going to go full-on detective mode and crack this case.
I mean, really think about what we're talking about here. These AIs are being handed the keys to the kingdom. They're acting as engineers trying to figure out why a website is down, or a security analyst patching critical software. They're even managing huge cloud budgets. The stakes? They're incredibly high.
So, here's the problem. The way we've been grading these AIs is just way too simple. We run a test and we get back a single number, a success rate. So we know that it failed, but that number tells us absolutely nothing about why. It's a total black box.
And you can imagine how frustrating that is. Developers just hit this dead end. Did it get confused? Did it make up a command that doesn't exist? Or did it just quit too soon? If you don't have those answers, trying to fix it is basically just taking a wild guess.
This is where things start to get interesting. What if we could go way beyond just knowing that it failed? What if we could get a detailed, structured report on the exact cause? What if we could treat every single AI failure like a crime scene?
Well, to do that, you're going to need the right tools. And that's exactly what researchers from IBM and UC Berkeley have developed. They've created this revolutionary forensic kit for AI, and it's called MAST.
And MAST is honestly a total game changer. It sifts through all the messy, confusing logs an AI produces and boils them down into what's basically a fingerprint. It can identify 14 distinct ways an AI can mess up, creating a unique failure signature for every crash. All of a sudden, we're not just staring at a failed mission, we're actually analyzing the evidence.
So with this new kit in hand, the researchers lined up their suspects. They took 3 different types of AI agents and put them under the microscope to see exactly how they break. Now, when you first look at the results, the story seems pretty simple, right? The fancy high-end model, Gemini, does really well with a 75% score. The open source models, well, they struggle a lot more. But trust me, that one number hides the entire story, the most fascinating part of all this.
All right, it's time for the interrogation. By using MAST, we can finally look past those simple scores and dig into the unique ways that each of these agents breaks down when the pressure's on.
And wow, this is where it gets really interesting. The data shows us not just if they fail, but the total complexity of the failure. Just look at the difference here. Gemini's failures are pretty surgical. It makes 1 or 2 specific mistakes. But GPT-OS, it has a cascading collapse, where one little error just snowballs into a complete and total system meltdown. This also highlights another key discovery from MAST. It turns out not all errors are created equal. Some flaws are benign, like the AI repeats a step just to be sure. The system can usually recover from that. But other flaws, they're fatal. If one of those happens, it's pretty much game over. And this lets us focus our investigation on the real mission killers. Okay, let's open our first case file. Suspect number 1, Gemini 3 Flash. This agent is incredibly powerful, highly capable, but it has one dominant personality flaw that brings it down. It's just plain overconfident.
So here's the smoking gun. When Gemini fails, there's a 52% spike in one particular fatal flaw: incorrect verification. It does all the hard work, gets really close to the solution, and then just confidently shouts, "Mission accomplished," without actually checking to see if it's right. It's basically grading its own homework, and yeah, it always gives itself an A+.
Next up, Kimi Q2. Now, this agent's profile is a completely different story. It doesn't have a problem with overconfidence. It has a classic case of analysis paralysis. It just gets stuck in its own head, overthinks everything, and then fails to actually do anything.
And just look at this number. It's wild. In 92% of its failures, Kimi K2 has something called an action-reasoning mismatch. What that means is its internal monologue, its thought process, is usually correct. It knows the right command to run, but when it's time to act, it does something totally different and usually useless. It's this huge gap between thought and action.
Our final suspect is GPT-OSS-120B. Now, this one isn't an overthinker. Instead, it just gets completely overwhelmed by the task, and then it forgets what it was supposed to be doing in the first place.
And this is a fatal flaw that's pretty unique to this model. In almost a quarter of its runs, it suffers from a catastrophic loss of memory. As the task goes on and on, it literally forgets the original problem it was trying to solve. The whole mission just goes completely off the rails.
So we've identified the culprits and we know their methods. But here is the real power of this kind of forensic analysis. It doesn't just tell us why an AI failed. It gives us a precise roadmap for exactly how to fix it. This is where it all pays off.
And the solutions are completely different for each agent. For the overconfident Gemini, you build an external verifier, you stop letting it grade its own homework. For the indecisive Kimi, you use a strict state machine to force it to act. And for the forgetful GPT-OS, you enforce what's called context hygiene to keep it from losing its memory.
So what's the big takeaway from all of this? First, that a simple success rate is hiding the real, actionable story. Second, you have to know if a failure is surgical or if it's a cascading mess, because that tells you how hard it's going to be to fix. And most importantly, diagnosing the specific way it fails is the only way to build a real targeted solution.
You know, this whole approach moves us from just blindly tweaking things into the world of precision engineering, and that's a huge leap forward. It leaves us with a really important question. Now that we can diagnose AI failures with this kind of accuracy, what does that mean for our ability to finally build systems we can truly, genuinely trust with our most important work?